Nice. Okay, so as I mentioned, the plan is kind of just to go through these homework assignments that I gave you. These are, assignments I gave out over the summer to my own students when I was teaching this class. But I think before we do this, or before we even start these, what I probably want to do is just like go through and show you like what I think should be on your equation sheets. Does that sound good? Are you okay with that? Does that mean you need to make them at some point anyway, right? So maybe it'd be a good idea to just knock that out. Cool. Okay. So let me adjust this. Okay. Exam view. Okay. That seems good. Nice. I also think I like enabled all the better Twitch TV emotes too, so I don't know. Feel free to use those, I guess. Um, okay, so the math stuff, right? Yeah, I am recording it. So I'm gonna post this to YouTube, so you can find it there. I'm gonna email everybody about that. It won't be on Canvas, but just check your emails. So let's see here. Okay, probably just like the math stuff first, right? So let's talk about the two kinds of vector products that we have, right? We have let me just say, or let me say this. Let me say vector multiplication because saying the vector product makes it sound like the cross product, right? So there's the dot product, right? And we can say something like for two vectors, right? Like A and B. The way that we want to calculate this is just multiplying the components, like the respective components, and adding them all up. So this looks like the x component of A times the x component of B plus the y component of A times the y component of B plus the z, if we have z components, right? The z component of A times the z component of B. This is, I think that this is pretty straightforward to calculate, especially if you have the vectors in terms of their components. And you can also remember that this is also given by the magnitude of A times the magnitude of B times the cosine of the angle between them, okay? And there's not really, I think, any physics here to discuss right now, even though we will use this for, physical quantities later on, but for the time being, it's just a math thing. Does everybody feel okay about the dot product there? I would say that you probably don't even have to have intuition for this, right? So the cross product you'll want to have a good intuition for, but dot product is it's just something to calculate at this point. Okay, let's talk about the cross product then. So what I want to do is I'm going to say A cross B, and the way that I would write this is AB sine theta, and then I would write n hat like this, where, let me see if I can do this. So n is perpendicular to both A and B. Well, n hat. Let me fix that. Now, so the important thing to remember about the cross product is the right-hand rule. This is how we determine the direction of n hat, right? And so let me try to put this in words. Let me say, like, take your right hand, point your fingers in the direction of the first vector, then curl your fingers in the direction of the second vector to get the direction of the, let's say, the resulting vector. And I would go through and do this, and we can do this for the example actually that I give you later on in the first homework assignment. But what it looks like is right hand, curl your fingers in the direction of the second vector. So like, let me try this again. So I'm pointing my fingers towards A. I curl them now towards B. Maybe B points like that. Your thumb tells you the direction of the result, right? So the idea is that it gives you a vector that's perpendicular to the two vectors you started with. It's perpendicular to each of them. Do we feel good about this, or would more details be helpful? Maybe what I will do is I'll just show you. What this might look like if you wanted to calculate it in terms of components. I'm not going to put this formula in the sheet because it's kind of annoying to copy, but I can make Mathematica take cross product for me, right? And so when I do the square brackets and an X or a Y or a Z, I already started doing this, so I'm going to finish it, but it's good. I'm happy to hear everybody feels good about this. So when I put the X or the Y or the Z in the square brackets, I'm just saying that's the X or Y or Z component of the vector. So let me just finish this up in case anybody does want to copy the formula down. But I'm just telling Mathematica to take the cross product for me, and then I'm going to have it express this as a column vector. And I mean, see, this is kind of ugly, right? It's like negative AZ times BY plus AY BZ, etc. This is your X component, Y component, and Z component. So if you want to, I'd say it's not a bad idea probably to have this copied down. And it's also in the textbook, I'm sure. All right, let's see. Okay, that's it for the cross product then and the dot product. Let's talk about kinematics. So I'll just write out the 2D kinematics equations. Generally, right, we have x as a function of time is just x naught plus the initial velocity in the x direction plus 1/2 a x t squared. This is probably one of the more important ones. And then we have, for velocity, we have the x component of velocity as a function of time is just going to be the initial x component of velocity plus the x acceleration times time. What is the other one? We have, I guess, this one. Right, and I mean, I think that's it. Like, there's the other one that is kind of just telling you the average velocity, but that kind of comes from, let's see here. That kind of comes from this. Now, maybe I'll put this down as one of my equations, even though it's more of a definition. I want to say that the average velocity is defined to be a displacement over a time interval. Let's say this is our fourth kinematics equation here. Let me make these pretty. Cool. And then, I mean, we just do the same thing for y, right? We can just go through, I mean, I could literally copy and paste this and just change all the x's to y's. That's what I'll do. Now remember, these are the general kinematics equations, right, for 2 dimensions. We're not talking about projectile motion just yet. And we will get to that pretty soon here, and then I'll just show you, I mean, you know, but I'll write down how these change and how I would put them on my formula sheet. So we're going to keep it general. And we're just changing all the x's to y's. Put a y there, and an x there, should be a y, Okay, cool. So now if we want to adapt these to projectile motion, so the assumptions that we make, right, about projectile motion will be that the acceleration in the x direction is 0, right? And that's we call that neglecting air resistance. And that the y acceleration is just the acceleration due to gravity. And so let me just say we have a sub x equals 0, and a sub y goes to negative g. And then, yeah, that's how I would write it, and that's what I'll do when I express these. So let's do this one first. We just get rid of this term because it depends on the acceleration, which we said was 0. This one actually doesn't tell us like anything very interesting other than that the x component of velocity is constant, right? And this one actually just rehashes the previous one, because obviously if v sub x for all time is equal to v naught x, then v sub x squared is going to be equal to v naught x squared, right? So we could just get rid of this. Where did that one go, though? There it is. Okay, cool. And then here, right, as somebody's saying, we just go minus 1/2. We replace this with a g. Turn this into a minus g. Now this one doesn't. Well, this one doesn't tell us anything redundant in this case, right? Like we found for the x direction here. So I would say this is a good one to have written down. And this I guess is still true, but I don't really know how useful it's going to be, so I'll just get rid of that. So did you want to see the x equations or the y equations, like the top y equation? For the person who asked me to scroll up. Cool. Okay. I think this all looks good. Does anybody see any mistakes? I do make mistakes from time to time, right? So just be vigilant. But I think that's it for the 2D kinematics, right? We've covered like the general case where something could be moving, say, on the ground as you're viewing it from above, where we can't say that the x acceleration is necessarily 0, and that the y acceleration is necessarily the gravitational acceleration. Well, so yeah, if you're asking about these equations, then yeah, these basically all have the exact same form, right? I mean, nothing changes from this set to this set except for all the x's become y's. But remember, this is not projectile motion, right? This is just general kinematics. I'm getting an email. Let me just make sure it's not anybody who has a question about what we're doing here. No, okay, cool. And so, again, like the way that you would think about these equations, maybe you could just imagine, I don't know, like you're looking down on somebody walking around in a field or something like that, right? And as long as they have like a constant acceleration vector, you could describe, you know, what they're doing this way. These equations will be just for the thing that we think about when we just like shoot a projectile, right, from say the ground with some initial velocity. And I mean, we'll do examples, right? So hopefully, if this stuff is not super clear, it will become clear in a little bit here. Let's just knock out like what we need for Newton's laws, and then we can, I think, start doing some problems. So neutrons, Newton's laws. The first one is like kind of whatever, right? It just tells us that, let's say, objects in motion tend to stay in motion unless acted on by an external net force, maybe. I mean, the idea here is just that the net force on your object is 0, it's going to just keep doing what it's doing, right? So I think that there's not really much. It's an important idea, right? But there's not really much practical use we're going to get out of Newton's first law. Now, the second law, though, is kind of everything, right? And the way that I would write this is I would just use a sigma to denote the sum, and this is a vector, of course, and this equals ma, right, where a is also a vector, and we're just talking about the net force on an object, and that this is equal to its mass times its acceleration vector, right? And this, like I said, this is really where most of the practical use for Newton's laws comes from. Now, we can talk about the third law a little bit because this could be useful too. So let me just say something like, if two objects are in contact and the first is exerting a force on the second, and I guess actually technically, right, they don't have to be in contact, right, because we'll talk about the gravitational force later on in the class, and there is no physical contact between the two objects, or two or more objects really in that case required, right? But for the time being, we'll say that this is just for when they're in contact. So if two objects are in contact and the first is exerting a force on the second, let's call this force F1 on 2. This will be my notation. Then the second exerts a force on the first with the same magnitude, but in the opposite direction. And like symbolically, we could write F12, equals, let me fix this. We're going to write negative F21. And just remember, right, that taking a vector and multiplying it by, let's say, -1, it just flips its direction, right? It's like rotating the vector by 180 degrees. No, I don't want this damn fraction to be stacked. Okay, cool. You know what, though, now that I think about it, coming back to kinematics, there is one more thing to discuss. Maybe we would want to have the range equation, right? So let's just get this down too. Somebody correct me if I'm wrong here, but I think that it's just this. Right, this tells us the horizontal range of a projectile. If we know its initial speed and the angle above the horizontal from which it's being launched. Now, I want to say, I'm sorry to come back to kinematics like this, but I want to say some important stuff about the range equation because students seem to think that it's, you know, super powerful and can solve all your problems, and it is useful, but the assumption here, let me say this, the assumption here is that delta y equals 0, right? So this means that your object starts and lands at the same height, right? So for a projectile that's launched from flat ground that, you know, undergoes some trajectory and then lands on flat ground again, this is great, right? But it won't work if your delta y is non-zero. So remember that because it's important. Okay. So then we got Newton's laws down. I think that's it then. Maybe unless there are like some specific questions that people have, we could just start solving some problems. I'll give you a second to say something if you have a question. All right, seems like no questions then. Have examples of worked out problems on the sheet. You're gonna have to ask Hadridge over that or about that because I don't I think that probably not, right? Uh, so I don't want to say, like you can or you can't because I don't know. I would assume not. This might be stupid, but there are any equations on forces? Yeah, no, that's not a stupid question because people will often be like, "Oh, what is the equation for tension or the normal force?" But like, there's no equation, right? It's just something that's there that we observe, uh, and so for a majority of the forces that we encounter, we just call them like the normal force or the tension force. And we know which direction they point, right? For instance, the normal force is always perpendicular to the surface on which an object is resting, and the tension force has to be directed along the rope, right? And it can only pull. But there's no like equation for the tension force or an equation for the normal force. Um, the one that comes to mind though that there is an equation for is obviously the weight of an object or the gravitational force on it, and that's mg, right? So I think that that is probably all you need. Organic chemistry tutor. I don't know if he's a chemist. I don't know if we can trust that guy. Okay. Um, so let's start solving some problems then. Let me see here. Okay. Okay, so the first problem I will probably not do because I would assume that everybody's okay plugging in the quadratic or using the quadratic formula, right? So we'll probably skip this one. How about number two? Do people feel like they need to see me do this, or should I move on? Because personally, what I really want to do, just because we don't have unlimited time, is maybe just work on 5 and 6 because I think these are going to be the most important kind of for your exam preparation, right? Because these are really the kind of the only 2D or truly 2D problems on this set that I assigned. Because this is kind of two-dimensional, but also not. But these two are definitely. Okay, so nobody's saying they want me to uh, do which one really fast. Yeah, yeah. Okay, and this is gonna be a little rough, and like honestly, part of the reason I don't want to do it is because like I'm gonna have to make a sketch, but we can just make a crappy one in Paint, and it'll be fine. Okay, so the first thing we want to do is just define our axes. So I will use the usual XY directions. And it drives me crazy when I can't get these lines perfectly straight. There we go. All right, so this is my Cartesian plane. Come on. Oh, okay, whatever. Uh, and let's like make rough sketches of these vectors. So I would say it's always a good idea to draw the vectors for problems like this. Draw as much as you can, right? So we have this vector u. This has a positive x component and a negative y component, right? So it's probably going to look, and I'll just use like a thick red line for this. We would go over 1 and then down 2, essentially. So it might look like this. This is u. And then v, right? V is going to be, if I'm not mistaken, in the third quadrant. We'll put this in blue. And you go to the left one and down 3. Yeah, okay, so look, don't worry about relative motion, all right? This is going to look like this. and I think this is a decent sketch. So what we want to do is we want to like draw in the axes that we're solving for. So I would just always use the angle that's somewhere between 0 and 90 degrees, right? And so for, why can't I change the color? There we go. So for V, I would probably use this angle. Let's call it theta. And for U, we'll use this angle, I'll call it phi. Now that we've made a sketch, we can kind of just get cracking on this. So for number 2, and I probably won't plug numbers in just to save time. But for number 2, what we would want to do is just solve for the angles. Now remember that if we're using or if we're thinking about an angle that's between 0 and 90 degrees, it's probably a good idea just to keep the components positive, right? So what I would do for something like this is I would say, let's see, I would write like tangent of phi for U, right, is just going to be opposite over adjacent. So in this case, it's just U sub y over U sub x. And maybe what I'll do is I'll put these in absolute value bars because I want to stress that we should focus on the positive values here. And cool. Now, this is going to basically tell us, right, that we can just arctan both sides. So we could write that the arctan here is going to give us phi. Now, this will definitely get you the correct angle as we've drawn it, but remember that in the problem statement I asked for the angle with respect to the positive x direction. So this should be, let's see here. Basically, what I'm trying to say is that our answer, right? If we say that our answer is like capital phi, that this is going to be 360 degrees minus phi. Now I wouldn't worry so much about this because, like, for an exam, right? It doesn't really matter how you express the vector's direction. I would say as long as it's clear to me what you're saying, right? And so, like, if you made a sketch like this, you drew in phi, then you could just be like, well, I know that phi is like whatever number of degrees, and I would be okay with that, right? I would have no issues with that. And I don't think that Hatridge would either. And so I would stop here and just, or I would actually probably just stop here, whatever number you get. Then you would do the exact same thing, right, for V. Like, really the important thing is to remember that if we're talking about angles between 0 and 90 degrees, then just keep the components positive when you're plugging your values into trig functions and stuff like that, right? Does this all make sense? Are we good with this? I would actually maybe like to talk about the cross product one really quickly though, because the intuition here is important, as I mentioned, so I think that it would be a good idea to just touch upon this at least a little bit, right? Now, the intuition behind, as I mentioned, right, the cross product is that it basically takes two vectors and it gives us a vector that is perpendicular to both of them, right? So if on the crappy sketch here, right, if I have my XY plane plotted, what are the possible directions that the cross product of these two vectors could point, right? There's only two possibilities here. Now, what are they? So remember x, y, right? Yeah, thank you. Into or out of the page, right? So you already kind of like know, just based on the intuition behind the cross product, that there's only two ways that the cross product of two vectors could point. Now, in this case, the way that so we could say, right, that we feel like the result here of the cross product is going to point in either the positive or negative z direction, right? And the way that we narrow down the choices is by applying the right hand rule. So what I want to say is that I take my right hand, I point my fingers in the direction of u, curl them towards v, and so now my thumb is pointing into the screen, right, or into the page. And that means that it should point in the negative z direction, right? And that's the most important thing here, because just figuring out what the magnitudes of each are and the angle between them is not, I think, terribly difficult, hopefully. But the direction is what I think could mess a lot of people up. So yeah, so we would say u cross v points into the screen. However, v cross u points out of the screen, right? So it's important to remember that the cross product, well, for taking cross products, the order is important. Let me see here. Maybe we could put that in the formula sheet. We could say that, like, because order matters here, we could say something like, if A cross B equals C, does anybody have any idea what I'm going to write here? I'm going to do this. I'm going to say that B cross A equals negative C. Just to stress to everyone that the order of operations is important when you're doing the cross product. And you can see this with the right hand rule. Okay, cool. Let's see, what else did you have to do for 2? Nope. Dot product. I think the dot product is pretty straightforward, right? Sum, right? You just add the components. That's cool. For the difference, you just subtract components, right? So it's kind of the same thing. It's kind of like the vector u plus the vector v for addition, and then it's like for subtraction, it could be like, you could say the vector u plus the negative of vector v. And this is a property that works for regular numbers, right? Like integers, for instance. And so I don't think that there's anything shocking about that, hopefully. Do we all feel good about subtracting vectors? All right, I am not seeing any responses, so I think at this point, let's move on. Let's do number 5. Okay, so remember that what I want to do is I want to make sure that everybody who's looking at my work understands what I'm calling things. So I'm just going to go through and do the symbolic stuff really quickly. We have the initial speed is 90 meters per second. The angle is 30 degrees. And the initial, yeah, no, there won't be any multiple choice. It's all going to be show work, yeah. I mean, which is good, right? Because multiple choice kind of sucks in a sense, because it's so all or nothing, I think. And I'm going to say that the initial y, right, which remember is that this we could write this as y of t equals 0 is h. And this is 1.5 meters. Okay, So we want to basically, I mean, we basically just want to solve for everything here, right? We want to figure out how long it's in the air for. We want to figure out how high it goes. And we want to figure out the velocity with which it hits the ground, the velocity vector, okay? So remember what I said, right? I've said this a few times now. I think that if you're like totally clueless about where to start with a two-dimensional kinematics or a projectile motion specifically problem, it's a good idea to just write this equation down, right? You write y of t, this is just the general form, is y naught plus v initial y t minus 1/2 g t squared, okay? And we know all these things, right? Like we know what y naught is. That's just h, or 1.5 meters. We have to do like a little bit of trig to get this, but I think everybody's probably comfortable with that by now. And this, the 1/2 g, of course, is just constant, and t is like sort of our independent variable here. So let's make this a little more specific to our particular problem. So I would write this. I would write y of t equals h plus, now we're going to write that the y component of the initial velocity is just v naught sine theta. And then we just copy the rest of the equation, basically, straight from like our formula sheet. So now we know, right? We know where this arrow is, or we know its y position at least, at all time, right? Because you just plug a t in, right? It'd be like 1 second, 2 seconds, 5 seconds, pi seconds, whatever, it doesn't matter. And you can get the numerical value for its y position. And so then let me just continue here and say, let's say the total time the arrow spends in the air is big T. Okay, so now we have to think a little more critically, because what we want to do is we want to just take this equation essentially and plug big T in. So we would say something like this. We would say y of big T equals h plus v naught sine theta big T minus 1/2 g big T squared. And you might be thinking, well, like, what does this do for me, right? Because this looks exactly the same as this. But the point is that we can now say that this equals 0. Because remember, big T is the amount of time for which the arrow is in the air. It's its hang time. And so we know that after big T seconds have gone by, the arrow is back on the ground again. What's up with not like this, dude? This isn't so bad, right? So, or is it because it's quadratic? Is that why you're? So I mean, the important part here, right, is that we wind up with this equation. We can even get rid of this thing here. It doesn't matter. And this is all we have to. We just have to solve this, right? And it's going to work out to be a quadratic, right? Because T is our, I would say this is like on par with the level of difficulty on the exam. Why does this seem difficult, or does it seem easy, or like what are we thinking? Okay, cool. So let's do this. I'm going to make Mathematica solve this for me because, like, why wouldn't I, right? So I just say, hey, I have a quadratic equation here, solve for T for me. And we get like this kind of disgusting expression. Now, we would probably want to evaluate this numerically, right? We'd probably want to evaluate this numerically to see like which of these times makes sense, because if one of these numerical values is negative, then it's probably not a good choice, right? Because negative time in general won't make a lot of sense. So let's calculate the number here. I'm going to just tell Mathematica what all the numerical values are. Theta is 30 degrees. V naught is 90. G is 9.81. And then H is like 1.5. I think that's everything we need. So let's see what we get. Okay, so we get like a non-physical time, right? This would be the negative time here. And then, let me just say, solving for t, we find, and I'll say that t is approximately equal to, let's say, 9.21 seconds. Okay, cool. So there's that, right? We got the first part. This is A. So let me just put, I don't know, let me put an A here. Okay, that's good. So B, let's see what we got here. The maximum height above the ground it attains. Okay, maybe, so then, since I think people feel good about this stuff, what do we think we want to do here then? Like, how do we get the maximum height? And while somebody's typing up a response, I'll answer this question. Would we be allowed to use a solve function on our calculator rather than writing out the quadratic formula on the exam? Yeah, that's fine. I mean, like, I've mentioned by now that I want to see symbolic work, but the one exception is going to be for quadratic stuff, because I trust that you know how to use the quadratic formula, and it's time consuming to use, right? So I would be perfectly okay if you just got a number. You just wrote on your exam, like, found roots using my calculator, and then just wrote the answer or something like that, right? Okay, but does anybody know what we want to do for part B here? Like, how do we figure out the maximum height above the ground that it attains? Who's got something? Because this is an important conceptual idea here. Yeah. Okay. So I'm seeing some good stuff here. In that one of these. Let's see. So first of all, you can't just plug t back into your equation, because this is the total time that it takes for its entire trip, right? So that wouldn't work, because if we plug big T in, if we plug in 9.21 seconds, we should just find that the y value is 0 at that time, because that's what we demanded here, right? Now, somebody else is saying plug in 1/2 big T, and that is close. But remember that the motion is not symmetric if the object doesn't start and land at the same height, right? So plugging in big T over 2 here is not going to work, right? So remember that for the exam, because that's a conceptual mistake that's easy to avoid if, I think somebody has stressed it to you. Let's see here. Add the 2 times given by the quadratic equation by 2, then solve the y of t equation. I don't even know if that would work, but maybe. But so the response that I like, though, is that v is 0 at the top of the parabola, but I do need to clarify that the y component of the velocity is 0 at the top of the parabola, right? Because the x component is going to stay the same. So how I would do this is I would say that there's some, let's see here, at y equals h, the y component of velocity is 0, right? This is what we want to do. Then we use this equation. We say v sub y squared equals v initial y squared minus 2g. Now, what is your delta? Because this is delta y in general, right? So what is my delta y here? I'll go ahead and say this is 0, because we're saying that the y component of the velocity is 0 at the maximum height. And I'm going to continue filling this in. This is just going to be v naught sine theta quantity squared minus 2g. Now, delta y is y final minus y initial, right? And in this case, y final is just big H, and y initial is little h. Because remember, it doesn't start on the ground, it starts 1.5 meters above the ground. So this is how we want to do this. Let's see here. So I'll just make Mathematica do the algebra for me. So I'm going to tell it solve this equation, just because it'll probably be faster and it won't make a mistake like I likely will. Because algebra is hard, right? I mean, okay, I think this looks good. So this is what we would find. After doing the algebra, we would find that big H is given by V naught squared sine squared theta plus 2g little h all over 2g. This is our answer. Do you guys want me to plug the numbers in? What do you think? All right, we're already started here, so we'll just do it. And I mean, here the numbers, like, you guys know I hate numbers and stuff, but here this could be just like a good sanity check to see if we get a reasonable value, right? Let's see here, V naught was 90. And I think that's everything. So we get about 100 meters, or 105 meters, well, 104.8, let's just say, one decimal place. But I don't know, this seems reasonable, right? Like, for like a really skilled archer, I guess. It's not crazy. If somebody else wants to like confirm that that's what they got, though, maybe that would be nice. Okay, cool. Does this all make sense? Like, I really want to make sure that everybody knows that the y, how did I say this? That the maximum height is only attained at half the hang time when you have your object starting and landing at the same height, at the same y value, right? And that's why we couldn't do that here. Because I know people, if there's a problem like this on the exam, I know people are going to try that, and it's just, you know, something that hopefully you know better than to do by the time we're taking the exam. Let's see here. Okay, cool. So I got somebody to confirm. So the last thing here is we just want to figure out what the velocity vector is, right? And I want to say that, remember, on the exam, it's important to read the problem statement carefully, because let's see here. If you, for instance, solve for the speed with which it hits the ground, then, you know, that wouldn't be full credit, right? Because we're asked for the velocity vector here. So we'll just look at the components. So solving for the components. We know that v final, which is, I'll just call it v sub x, is just v initial x, right? Which is, of course, v naught cosine theta. We'll get a number here for all you numbers people. So 90 times cosine of 30. Okay, that's helpful. I love it when it does this. Okay, so we're getting about 77.9 meters per second for the initial x velocity, and indeed the x velocity at all times, right? Because that's our assumption about projectile motion. Now, for the other one, there's a little bit more involved, right, in terms of finding the y component of the velocity, and I would say that the way we want to do this is we want to use the time that we found in part A, and we would just write this. We would write v naught y minus g big T. Now remember, v naught y is just v naught sine theta minus g big T, and we could just get the numbers here too. So let's do 90 times the sine of 30 minus 9.81, and then we found 9.21. So it should be about, let's say, negative 45.4 meters per second for the y component. Okay, cool. And that's it, right, for this problem. So does this all make sense? Is everybody good with what we did here? I'm kind of tempted to go back up to the beginning of the document and just make like a quick list of the most common conceptual errors that I see people make for these topics. Is that something people would be interested in seeing, or should I just keep doing problems? All right, wait a couple more seconds, and if I only have one person say yeah, I'll probably do it because, okay, cool. Okay, cool, good. I think this would be a good thing to discuss. So I'm going to do this. I don't think we need the document. So let me say common conceptual mistakes. And we'll put the incorrect idea, and then we'll put the correct idea. So the first one would be, let's say, this is easy. I don't think I have to really justify this too much, but that the velocity is 0 at the object's maximum height for projectile motion. So this is the incorrect statement, right? Because the correct statement is that the y component of the object's velocity is 0 at its maximum height. So I'll just like cross this out or something, so we all know that this is the incorrect one. Cool. Okay, this is a big one. I've seen so many students do this. Okay, let's talk about projectile motion some more. So the incorrect statement that I have in mind here would be that if an object is undergoing projectile motion with hang time big T. Remember, hang time, right, is just the time that it takes for the object to go from its starting position to its final position. Then it attains its maximum height at, let me say, time t equals big T over 2. So this is incorrect, right? We were just talking about this one also. So I'm going to put a line for this. And then I will just say, if an object is undergoing projectile motion with hang time big T, then it attains its maximum height at time t equals big T over 2, only if, and we'll just say delta y is 0, right? Because what we're saying here is that it starts and lands at the same height, right? And we talked about this in the problem we did. We talked about this also when we were discussing the range equation, right? Let me just make sure I'm not saying anything inaccurate or incorrect here. I think this is good. Cool. Let me just do this too really quickly. I'm going to say the range equation as stated in class, because you know there is another formula for the range equation that always works. Let me see if I can find this because it looks awful. So if you want the form of the range equation that always works, it's this, right? This is the one that we're talking about. So I just want to make sure that everybody knows this is the one we're talking about, not this one, because this one actually will always work for you if you're neglecting air resistance. So the range equation, as stated in class, always gives the correct horizontal distance the object travels. And so let me be efficient here and copy this before I put the line through it. So this is incorrect, right, because the range equation is stated in class. Only gives the correct horizontal distance the object travels when delta y equals 0. Okay, cool. I think that's it for kinematics. I mean, these like I said over the past 2 years that I've been taking for this class, these are some very common mistakes that students have made. So I want to make sure that nobody's making these, right? Because if you can just avoid making these, like, I know this might not sound like a lot, but you're at least guaranteed to not get the lowest grade on the exam, right? And I would say you're probably better off than a lot of people. Okay, so let's talk about like the conceptual mistakes we might encounter when working with Newton's laws. Here's an easy one, I think. So the normal force always points straight up, right? And this is not correct because it depends on the surface on which the object is situated, right? So this is incorrect. And the correct version would be that the normal force always points perpendicular. And we say perpendicularly away from the surface on which an object is resting. I don't think I probably need to say too much more about this. Maybe the last one would just be about tension, right? And this is something that we all know, but can be easy to forget in the heat of the moment. But we want to remember that tension can only pull, it can't push, right? So I don't know what the wrong statement here would be. Tension, I don't know, maybe we could say it's like just, all right, I'll write this even though that seems kind of silly. And this is incorrect, right? So we're going to say that the correct statement is that tension can only pull on an object. And I think that these are probably like the big 5 that I've seen. Yeah, actually I like that one too. So maybe we could come back to, we switch this up. We could make this number 5, this number 6. And we could say number 4 here. We always use cosine for the x component of a vector and sine for the y component. And this, our decision to use either sine or cosine for the x or y component depends on the reference angle, right? So somebody's asking if I could explain number 2. Yeah, we can talk about that. Give me 1 second here. So when we have let's say symmetric projectile motion, right, which means that our object starts and lands at the same height, we have a lot of nice symmetry, right? Like we have, for instance, that it reaches its maximum height at half the hang time. And also we have, for instance, well, so we could derive like a nice expression for the hang time of the projectile, right, using the y of t equation. Uh, and we can't do those things if the object does not start and land at the same y value, right? So if you have a projectile that's being shot, say, like off a cliff and lands in I don't know, a river below or something like that, you can't make these assumptions um, because it's not symmetric, right? Let me think about this for a second. Because like, look, if I can make a crappy sketch here. Let's say we have like projectile motion. An object is shot from the ground at some velocity, and we know that its path through the air is going to look more or less like a parabola, right? Now, one of the nice things that happens here is that we have that the final uh, y component of velocity is just the negative of the initial y component, right? This would be like another nice thing that comes out of this symmetric projectile motion. But now if we think about like a different case, right, where like for instance maybe it starts at some height and it has the same initial velocity and whatever, but like it lands now lower than where it started. We should be able to see from this, for instance, that like there's no way the y components of the final velocity can have the same magnitude as the initial y component, because there's more time here for the gravitational acceleration to act on our projectile, right? So, for instance, like its final y velocity can't have the same magnitude as the initial y velocity, whereas like here it can, right? Because it's launched up, the gravitational acceleration has some time to act on it. It hits a velocity y velocity 0 at this point, and then the gravitational acceleration has the same amount of time to act on it, except now our velocity vector and the gravitational acceleration vector are pointing in the same direction, right? And so the thing is, just remember that, like, really, if you can just remember that there are lots of nice things that happen when we have objects undergoing projectile motion and starting and landing at the same height, and that things aren't so simple when the object lands at a different height than the height from which it starts, right? Is this helpful? Is it a little clearer now, like what I mean by this? Okay, cool. And like I said, I've seen so many students mess this up over the years that I just want to make sure that none of my students does this, basically, right? Okay. Let's see. Okay, so then getting back to maybe solving some problems, do we want to do number 6 here? Or do we want to move on to Newton's laws? Forces, yeah, okay, so at least one person wants to do forces. Mm, let me see what we have. Both? Okay. All right, well, let's do a force problem, and then we can come back to another kinematics problem if we feel like there's time and we want to. Okay, so this is problem number 8 from chapter 5. Let's see what this is looking like. I think that this one is a little on the simpler side, but this might be good to do just so we get some practice with vectors and stuff like that, right? So I think let's just try to knock this one out really quickly here. Okay, so 5.8. How do I want to write this? I don't want to write unit vectors because there's no reason for that. So I'll do my ordered pairs thing here. We're going to have that this vector is, well, it has components like so. 6 meters per second squared. Cool. Cool. Remember that my convention is just, when I'm typing at least, to write it, I don't want to do this here, bold and unitalicized, right? So this is what we have for the acceleration vector. Now, we also have these other forces in terms of their components. So we have 30.0 newtons for the x component of the first one and 16 newtons for the y component of the first one. This is a vector. And then we have one more force. Negative 12.0 newtons and 8.00 newtons. Cool. Okay, so this is really just sort of getting some practice with Newton's second law mostly, right? Because remember, right, from Newton's second law, we said something like this. I didn't need parentheses there, actually. There we go. Typing is hard. Now remember, right, that this gives us at minimum usually a pair of equations, if not a trio of equations. So what I want to do is I want to just write out the equations separately, right? So in the problem we have three forces, right? We know the acceleration that the object is experiencing, and we know two of the three forces on it. So what we could write here is something like, well, the x component, it's in bold, of the first force plus the x component of the second force plus the, and I'm going to get rid of the bold in a second here, x component of the third force equals the object's mass times its x component acceleration, right? Now, I'm talking about components here, so I no longer need to use the vector notation, right? Just in case that's not clear to anybody. And we're going to have like an exactly analogous equation for the y components, right? We just change everything to y, all the x's to y's, and we're good to go. So that's that. Let's see here. So then, I mean, it's really just doing the algebra. It's like just saying, we take this equation, this first equation here, and we just isolate, right? We isolate f sub 3, the x component of f sub 3. So I just subtract f1x and f2x, right? It's just algebra. And then, I mean, really, we're just going to do the exact same thing for the y. And that's it. I mean, you just have to be careful with your signs, right? Your SIGNs, because you know, you don't want to put like accidentally put, you know, an extra negative in there, or take something that's negative and make it positive, right? So you just want to make sure that you're being very careful doing the algebra. But this is all you do here. And I mean, they don't even tell you how to specify the force, so I would say for this one, expressing it as an ordered pair is probably perfectly okay, right? So we would just write this. We would just write that F3 equals F3x, F3y, and these values will just work out to be whatever they are. Cool. Okay. I'd assume everybody feels good about this, right? I don't think there's really any punches being pulled or tricks here. right? So if you're not feeling good, let me know, but I'll just assume for now that everybody is okay with that. We move on to number 34. See what I asked these people to do. Okay, this one, I think this one is pretty good because uh, we're probably used to the force being applied in like a problem like this, such that it's directed along uh, the slope of the plane, right? If we have a box on an inclined plane or something. So let's talk about this one. I think what I want to do here is just this. So I'm just copying basically the picture from the, oops, not that. Copying basically the picture from, wait, what the hell is happening? There we go. ProStreamer, by the way. This is what I want to do. So we can just make our free body diagram on the diagram that we're provided, if I can find where this thing is. And this is probably good. Okay, cool. So let's talk about the forces that are on this thing, right? So this is 5.34. I'll do this stuff later. We have a force that's given. I'm like tempted to try to zoom in a little more, but I feel like I'm going to lose. Okay, that's probably fine. So we have the force that's given, right, which is just in the problem statement. So we know what that is. We know that it has. Well, do they tell us what the magnitude is? No, we have to solve for it. But we know the direction, right? So we just filled this in. We want to put in the gravitational force. Now remember, this is always going to point straight down, regardless of what kind of a situation your object finds itself in. So we could draw that in like this maybe. This is my gravitational force, pointing straight down. Okay, and let me try to write with my mouse here. That's awful. And then we'll do the normal force, right? Now this is one of the situations where we want to remember normal force doesn't point straight up, it's going to point perpendicular to the surface. So let's try to draw that in as well as we can. And I would draw it like this maybe. Cool, that's my normal force. And I don't think there's friction in chapter 5. Yeah, there's no friction. Okay, so let me just summarize what we know. We know the mass of this thing, and I'll bring the diagram back up in a second here if people want to still copy that down. And we know that the angle is 30 degrees. Constant speed. Okay, so what I would say actually before we do anything else is I would say that constant speed tells me, right, that my acceleration vector is just 0, 0, right? So that's another thing. We're not given, like a numerical value explicitly in the problem statement, but we have to just sort of read between the lines to see that. Okay, so remember that the first thing we want to do, right, is we want to define our x and y directions. And somebody was asking me about this one earlier, actually, and I think here it would be okay if you use the regular xy axes, but I am inclined to rotate my axes. So what I'll do is I'll put a black line in. This is going to indicate my positive x direction, right? So it should be just sort of along the surface of the ramp. And then I'll put another one in to indicate my y direction, like so, okay? So I've specified my axes now, which is one of the first things you want to do. And we should probably do like a little bit of trig too, because we want to make sure that we get like these angles correct. Because there's two different angles here that we kind of need to make sure that we're good on. So the two angles that I'm talking about, right, would be this angle and this angle. Now, these are both theta, right? Is everybody okay with that? Like with how I can just say that they're both theta? They're both the 30 degrees? Or do I need to talk about this? It's okay if I do. I don't mind talking about why I know they're theta. I've had a few people ask me about this, so like what I'll just say is that it comes down to this idea of mutually perpendicular axes, right? Yeah, of course. So the two axes that define the angle that we're given, right, are basically, we'll say the ground, and then the surface of the ramp, right? So those are the two axes that I'm talking about for the angle theta, right? The one that we're given. Now, what are the two axes that define my gravitational force vector, right? They're going to be the gravitational force, which points straight down, and then let's say the negative y-axis, which points like this. But if my positive y-axis is perpendicular to this surface, then my negative y-axis is also perpendicular to it, right? So what we see is that the negative y-axis here is perpendicular to the surface of the ramp. And the gravitational force is perpendicular to the ground, right, which means it's perpendicular to this other axis that defines theta. And so this is theta, right? Mutually perpendicular axes mean the angles are the same. It's just a geometry thing that I know people probably haven't thought about or used in a long time, but it is important. Now this one hopefully is clear that this is theta because here I have basically this force vector, which is one of my axes that is obviously parallel to this axis on the ground, and then I have this positive x-axis here, which is obviously parallel to the surface of the ramp. So this angle and this angle must be the same. And you know, it's not a bad idea to like make a really clear sketch because this can help you see this stuff, right? So I mean, like what I used to do when I was like in the intro classes is I would literally use a ruler to make my free body diagram, right? It's kind of a nerd, but I think it helped. So yeah. Okay, let's solve this then. Actually, I think I still need this. So I mean, the blueprint here is right, just sum forces. And so if you have a problem involving Newton's laws and you don't really know what to do, it's never a bad idea to just start summing forces. So let's talk about summing forces in the x direction. What we're going to do is we're going to say the net force in the x direction is just, let's see what we have here. So we have a component of the applied force, right, which should be given by cosine in this case. Should be F cosine theta. Now, the thing that you need to remember about rotating your axes is that you will often, almost always, I would say, have a component of the gravitational force in your x direction. And this is easy to forget, right, because it's not what we're used to when we talk about the x-axis just being horizontal and the y-axis being vertical. So we would have to subtract off the x component of the gravitational force. And in this case, it's going to be sine theta, mg sine theta, right? Now, remember, this equals the x component of the acceleration, but the x component of the acceleration is just 0, right? Because there is no acceleration. It's moving at constant speed. Okay, so that's cool. And then we want to look at the y direction. Now, the normal force here is pointing perfectly along the direction of the positive y-axis. And we just have to remember to take the component of the gravitational force that points in the direction of the negative y-axis, right? So this looks like big N minus mg cosine theta. And this is also 0, right? Because our acceleration vector is 0. So all of its components are 0. And that's, let's see, what do we need to do here? We need to figure out what the applied force is, right, to make the acceleration 0. And so I don't think we even need the y equation here, but it's not a bad idea just to have written it down for practice. But we focus on, let's say, focusing on the x equation. What we would find then is that f equals, after doing the algebra, right, mg sine theta over cosine theta. And this should just be mg tan theta, right? Because sine over cosine is tangent, and that's it, right? Does this make sense? Does anybody see a mistake, by the way? This doesn't seem too terrible. So we'll get a number here. It's going to be 100 times 9.81 times the tangent of 30 degrees. And I want to remember to tell Mathematica to give me a decimal, not the exact value. Okay, so 500, let's say 566 newtons approximately. Yeah. Cool. Okay, does that all make sense? Is this one good? Are there any questions about it? I think we have time for at least one more. All right, not seeing any questions, so let's look at the next one. That was 5.53. Let's see what we got here. Oh, this would be a good one. Yeah, because this is sort of like a Newton's third law thing, in the sense that the tension is the same at all points along each rope, right? So let's do this one, unless everybody feels good about it and we want to look at another one, but I'm inclined to maybe go through this. All right, I'm going to start doing it then. So I would say for a problem like this, 5.53, let's see what we're given first of all. We're given some tension, 65 newtons. We're given a mass, kilograms. Okay, cool. Yeah, I'll definitely do it. 31 kilograms. I think that's it, right? Yeah, we don't have anything else. Okay, so I don't think I'm going to draw the free body diagram here, just because it's going to take time, and I think that hopefully you'll be able to see what I mean when I just sum my equations. But if anything's unclear, or when I sum my forces, I mean. But if anything's unclear, just let me know. And I'm just going to do this all at once. I'm not going to do A, B, C. We'll just solve for everything, right? So let's say the only force in the x direction on the first mass is a tension force, right? So what we can do is we can just say sigma F in the x direction on the first one is just T1, and this equals M1. Now they're all connected, right? And they give you a hint here in the problem statement. They say the magnitude of the system's acceleration. So we're just going to, we're going to assume that the acceleration is the same for all of them, right? I think that's a reasonable assumption. If you imagine, for instance, like doing this, right, like taking some boxes, tying them together, and then pulling on them, you would see that they're all kind of constrained to move in the same way, right? So, and that's it, right? Because realistically, the only other force here we could have would be like friction, maybe pointing in the other direction. and we're told the table is frictionless, right? And friction won't be on the exam, so it all works out. Okay. So let's look at the force, the net force on the second one in the x direction. This is a little more interesting, right? Because now we have the T2 pulling on this to the right, but we have T1 pulling on it to the left. But this is still going to have this ma term over here, right, just from Newton's second law. And as we were just discussing, these accelerations are the same, right? So that's that. Let me see here. Is it all making sense so far? Cool. Okay, so let's look at this third one then. Now we're going to have T3 minus T2. And this equals M3A. Because now the rightmost block is being pulled right due to the fact that it's connected with a rope to the second block, the middle one. But it's also being pulled on the other end by the hand, right? And so this is what this should look like. Okay. So, I mean, at this point, like, if we're all good with these equations, right? And I'll just keep talking, but obviously say something if anything about this is unclear. I mean, at this point, it's just a math problem, right? We have 3 equations and 3 unknowns, right? We have the acceleration to solve for, we have the first tension to solve for, and the second tension to solve for. So we do algebra, right? Doing the algebra. And I'll do this myself because I think that it might be, let's see, it might not be 100% clear if I just make Mathematica do it. So why does block 2 and 3 have 2 negative tensions? Let's see here, block 2, block 3. Well, okay, so remember that tension can only, so we want to remember 2 things about tension, right? We want to remember, number 1, that it can only pull. And we want to also remember that the magnitude of the tension force is the same at all points along the rope, right? And so those are the only 2 ideas here that we really need to see that our equation should look like this. Now, we're also making the assumption that this whole system is kind of accelerating at the same rate, right? But that's not even that big of an assumption because we're kind of told in the problem statement, right? The magnitude of the system's acceleration, which pretty clearly, I think, indicates they're all accelerating at the same rate. Let me see. So when we write out the math, you want us to keep the units the whole way through. Well, you know, you can do math with symbols, right? You don't have to have numbers to do math, but I would prefer that you did. Yeah, I would like, so remember what I was saying, right? As soon as you plug the numbers in, I want to see units, and this will potentially stop you from making a mistake, right? Like I would almost guarantee that at least at one point in the semester, keeping careful track of the units will save your ass, right? So it's a good idea. But if you just could do the symbols and then, you know, plug the numbers in at the very end, then that's better. So wait, in the second equation, is that an equal in front of T2? This, I don't know if it helps if I zoom in, this is a minus sign, but this is an equal sign. Yeah, so equal sign, equal sign. Cool. Actually, I'm just noticing that that's a little unclear when I look at the window here. That's not good, but hopefully, like, yeah, I don't mind clarifying, and you're listening to what I'm saying, I'd assume, so it's hopefully not too confusing. Okay, so algebra, right? We got to do it. Let's see what we want to do here. I would say that the sensible thing to do here is to solve, I'll put this in the document, we solve the third equation for T2, right? So we would find that T3 equals T2 plus M3A, and then we just subtract M3A from both sides, right? So that's T2, and I want to write this the other way because it's like that. And then we just plug this in to, then plug this in to the second equation. So T3 minus M3A minus, oh wait, no. No, this is good. I'm confusing myself. T1 equals M2A. And so now, right, well, we need to do one more thing here, actually. I'm going to say we finally plug T1 equals M1A into the previous equation. So we end up with T3 minus M3A minus, now T1, right, from our net force equation is just M1A. And this equals M2A. So, I think I can do this in my head, though I'm not sure. What we would find is that T3 equals the sum of the masses, right? M1 plus M2 plus M3, all times A, right? We just add all the MA terms to the right-hand side. And we then find that our acceleration is equal to the tension divided by the sum of the masses, right? And I don't think I'm going to get a number here because this would be one of the ones that's in the back of the book, right? It's an odd one. Do you guys, this is the same book you're using for the class, right? Just to be sure. The Halliday and Resnick. Okay, cool. All right, good stuff. So then I'll just, excuse me, I'll just leave this symbolic. So with A now known, right? With A now known, we wanted to find T1, right? We just had from our equation before that T1 equals M1A, right? So now we know T1. We just, whatever, number we got here, we just multiply it by the mass of the first box or block, and then we have T1. So we've gotten the acceleration, we've gotten T1. Let me say, to get T2, we turn to, and what we want is this equation. And T3 is given in the problem statement. We've already solved for the acceleration, so we have everything. Right? So I haven't explicitly gone through and like calculated what you're supposed to get here, but like we in principle now know all this stuff. Is this clear? Does everything about this make sense? There might be, so there could be some like fancy shortcuts you could take to simplify this problem, but what I would say is that it's not necessarily a bad idea just to look at the net force on each object in your system, right? I think that that's probably a good way to go, and that's what we did here. Now, I mean, I didn't write out the y direction because nothing really is happening in the y direction, but if I wanted to be like thorough here or whatever, I would have written the y direction also. Couldn't T2 equal into a plus T1. Let's see, is that one of our equations? Yeah, wait, did I write that? Maybe I wrote it wrong. Maybe I did mess this up. What was I doing? Yeah, okay. No, I think what I wrote is fine, and what you're saying is also fine. There's, at this point, like, there's more than one way to get it, I guess. And it would be a good idea, right, to check to make sure that you get the same value doing it both ways, because that's how you can be reasonably confident that you did it correctly, right? So if you find yourself with extra time on the exam, I would say definitely go through um, and check yourself. Oh, let's see. One with a pulley. I'm kind of out of time here. Um, let's see. Okay, what I'll say is if you pick one from the book that you'd be interested in seeing me work, I will try to find time to maybe work it out in like a YouTube video and post maybe sometime tomorrow. So just like hit me up, right? Let me know which one you'd like me to do, and then I'll try. No promises. I'll try to make a video. And like what I would like to do also is go through this document and like clean it up, make sure it looks all nice and stuff, and then send it out to everybody if you're interested in having it, right? Uh, and that's something that I could also do if people want it. Um, but I do need to get going, unfortunately. I would like to help more, but I have class. So, yeah, cool. I can send this out to everybody. Um, yeah, and so if the exam's on Wednesday, right? If you need anything, hit me up. I'll try to help you as much as I possibly can, and I'm sure you're all gonna do awesome. Uh, yeah, I will see you. I will see you on Wednesday then.